Hello friends, welcome to UGC PG Pathshala. I am Dr. Lubna Siddiqui, Assistant Professor, Department of Geography, Jamia Millia Islamia, New Delhi. Today I am going to discuss about the module Data Processing and Frequency Distribution, which comes under the paper Quantitative Techniques in Geography. Now, introduction. Quantitative information is main component of scientific inquiry. After collecting the data of a geographic attribute that is called variable, either from the field work as primary source of information or secondary official sources, it has to be processed and arranged orderly in accordance with the purpose laid down for the inferences of facts for scientific explanation. Collection of data and its reliability is one of the dimensions of discussion which is not discussed here. But after collecting the data, there are three following given processes of data operation to make it more organized for further statistical operations. Number 1, editing. After collecting data, the examination of collected raw data, especially from field survey, is to be edited to remove errors and to correct the data for further use. Field surveys are conducted through developing schedules or questionnaires. Sometimes field editing is also done when a team of collectors of data visits to the field and observes the data errors which deviate from the eye-seen realities of an object for which quantitative data are collected. Editors may correct many entries of data in the field itself after observing the reality or determining error after getting proper answer from respondents in the field. Second step of editing of the collected data is known as central editing, when data are collected through schedule from the field and returned to concerned office for final processing. Editors convert data keeping in mind various aspects of data arrangement, such as data entry in the wrong place in the table and utilization of data, that is whole data of a variable, to be converted into the same unit. For example, income per household is given month-wise in the printed schedules, but some of them provide information at different scale of time as yearly income. This is the task of central editing cell in the concerned office to convert income data in the same unit of time, either monthly or annual income of a household, by converting it linearly or curvilinearly as per the requirement for fact-finding reports. Number 2, coding. It is necessary for efficient analysis and correct findings of observations. The transfer of raw material of filled schedule into the numeric form that makes limited categories of variables or characteristics of given data for further computation and data processing is an essential part of the process of data arrangement. Many research scholars used earlier the hand coding method to keep information in proper arrangement. Coding sheets were used to complete the data arrangement due to availability of modern tools for coding and computing data. The coding processes is nowadays more efficient and correct to find out results when 1 BM computation process stored in 1980s. The punching cards were used to arrange data sheet. With advancement of new softwares like Excel sheet, the coding and processing of large chunk of data become easily and fast. Now 3, classification. Most research studies are nowadays dependent on large volume of data which are available from various advanced sources like remotely sensed data of spatial attributes, data generated from topo sheets, field inquiries, and so on. Such large volume of data is classified based on homogeneous groups of variables or common characteristics of geographical factors or attributes. It is called the statistics of attributes. On the other hand, since geographical analysis are more concerned with the area or places, the homogeneous classes of data may also be made based on homogeneity of places or areas to synthesize it. Classification of data either based on characteristics, that is variable features, or based on place, that is observation. Classification has its own importance in inferring facts. Classification is utilized as tool in geographical studies in a variety of ways. Number one, in regional planning and development, the concept of compage, that is togetherness of characteristics, and fusion, that is interaction of different spaces, are largely dependent on the process of regionalization. It is dealt with the dimensions of geographic data, matricas. It is dealt with the dimension of geographic data, matricas, described in another module entitled Geography and Quantitative Techniques. So, classification is a source of regionalization. Areal homogeneity within and heterogeneity between the areas is a fundamental principle of regionalization, which is operative only through the concept of classification. Second, of course, there are two types of statistical procedures to handle a set of data. The ungrouped data set operated with simple statistical techniques, that is used for a small size of sample set as n less than 30, where n is number of observations or items in a data set, and the group data, that is called frequency distribution, used for larger size of data set as n more than 30. The problems of frequency distribution are always kept in mind when classes of the magnitudes of variable are chosen and class limits are fixed. Number third, grouping the larger volume of a set of data is related to frequency distribution. Group data tables are called frequency tables. It is an essential processing of data for statistical operations as well as for mapping the geographical attributes. Number of observations I falls under a given class is known to be the frequency of that particular class. Selection of class interval and number of classes usually involve three problems. Number A, how many classes should be for a set of data. Number B, how to choose class limits, and number C, how to determine the frequency of each class. Such problems of frequency distribution and its application in geographical researches are discussed here in the following parts in detail, with giving examples from geographical studies. Although there is no specific answer to the above cited questions, there are some suggestions given below. Sometimes we have more number of classes to make frequency distribution table. However, 5 to 15 classes are reasonable good to understand the variability of distribution. In general, the following formula provides rough guidelines for deciding the class number as well as class intervals or preparing any frequency table. N is equal to 2k, that is, as this is shown in equation number 1, or k is equal to 1.0 plus 3.0 log 10 n, as it is shown in equation number 2, where k is equal to number of classes to be used in a frequency table, n is equal to total number of observations, and log 10 is equal to logarithm to the base 10 of number of observations according to PAL 1998. In addition, width of class called class interval is determined by dividing the range of data series, that is maximum minus minimum value of data set, that is R, by number of class k, written as I is equal to R upon 10 plus 3.0 log 10 n, as it is shown in equation number 3, where I is the size of class interval, We indicated earlier that it gave rough estimation of calculation of number of classes, but it is purely objective to make classification because the nature of distribution of data set may be different and skewed. Sometimes we have to avoid general principle of equi-interval classes due to large variation in given set of data. It may clearly be understood by giving the example of daily rainfall precipitated in Cherrapunji, that is most humid place on the earth. Now example, daily rainfall data of 211 days from 20th March to 16th October 2004, that is rainy season in Cherrapunji area, in which 41 days were counted as zero rain days. Remaining 170 days had daily rainfall more than 1.0 mm. A total amount of rainfall of 14,719.3 mm was precipitated in 170 days, with a large variation ranging from 1.0 mm to 793.2 mm as shown in Table 1. Table 1 shows collected daily rainfall data of 21 days, that is from 20th March to 18th November 2004 at Cherrapunji. As per the application of given formula, that is equations 2 and 3, a total number of classes were calculated 8 and size of class interval was approximately 100.0 mm because k is equal to 1 plus 3.3 log 170 is equal to 8.36 number of classes and I is equal to 792.2 upon 8.36 is equal to 94.76, that is approximately 100 mm. Following calculated number of classes and their sizes, a frequency table is prepared with the help of filtering the given data of rainfall through the use of Excel sheet Microsoft. A discrete frequency distribution is given below in Table 2 and Figure 1. If this data of continuous series of a small scale interval of frequency distribution is shown by a smooth curve, it is called frequency curve. On the basis of the curve shape, the frequency curves are divided into 6 different forms. Number 1, symmetric, that is normal curve. Number 2, positively skewed, that is concentration of frequencies towards lower magnitude of classes. Number 3, negatively skewed, that is concentration of frequencies toward higher magnitude classes. Number 4, J-shaped distribution, that is as frequencies are concentrated in the higher value classes. Number 5, reverse J-shaped distribution, as frequencies are concentrated in the lowest value class as shown below in the frequency distribution of Cherrapunji rainfall. And number 6, U-shaped distribution, that is if it is inversely to the normal curve. Measures of this distribution would be given separately in another module. However, an interpretation of rainfall table is given in the following paragraphs. And number 6, U-shaped distribution, that is if it is inversely to the normal curve. Measures of this distribution would be given separately in another module. However, an interpretation of rainfall table is given in the following paragraphs. Table 2 shows frequency distribution of daily rainfall data following the equal interval classes, that is total 170 days. Please note 0 rain days are excluded in this distribution. This table compiled from the data given in Table 1. Distribution is discrete because each class of it does not have common value of class limits. Figure 1 shows frequency curve of the daily rainfall at Cherrapunji. From the frequency table of rainfall, it is obvious that most of the frequencies, that is 133 out of a total 170, fall within the category of 1 to 100 mm. It is reverse J-shaped distribution. Of course, a distribution having almost equal frequencies in its each class is said to be the ideal rather than the groups classified by following the given equation 3. Sometimes the formula of identifying class numbers for frequency distribution does not give proper result. It may be due to a large range of magnitude of given data. In such a case, either the equi-interval of the classes is to relax or data series is to be transformed to logarithmic system to examine the real nature of distribution. For example, the same data set is transformed into log 10 system and then classified into classes as per the convenience of data variation. In the present case, an equal class interval of 0.40 of the log of rainfall. It gives better results as frequency distribution follows its normal tendency as shown in table 3 and figure 2. Table 3 shows transformed frequency distribution, whereas figure 2 shows graphical representation of transformed frequency distribution, that is daily log rainfall in Cherrapunji. Now, cumulative frequency distribution. Frequency of each class in the distribution is often facilitated to understand their cumulative effects as and when it requires, that is mathematically called the integration of frequencies to obtain combined effect of an event or variable's trend. In fact, cumulative frequency curves, that is called ogive, is S-shaped and always has increasing trend if class frequencies are cumulated at a less than basis. Inversely, this curve is reverse S-shaped if more than rule of frequency accumulation is followed as shown in table 4 and figure 3. Table 4 shows cumulative frequency distribution, whereas figure 3 shows ogive of daily rainfall at Cherrapunji. Now, characteristics of frequencies distribution. A few following points are important to note when one must use frequency curve. Number 1, area of the constituent rectangle of a histogram is proportional to the number of frequency falling in the same rectangle, that is bar. Number 2, if a perpendicular is drawn from any point of the frequency curve to x-axis, the area between x-axis and frequency curve becomes proportional to the number of observations. The curve of a distribution is called density function. Number 3, relative frequency shows concentration of frequencies in the distribution. It is calculated by dividing frequency of each class from its total. It can easily be converted into probability distribution as shown in table 5. Table 5 shows relative frequency and probability in different rainfall classes at Cherrapunji. And number 4, cumulative frequency curve is useful for determining the quick graphical procedure for finding the median and any percentile measures, including the quartiles. However, more than and less than curves interact at median of variable data. The point of less than cumulative curve, which interacts the 50% frequency of the distribution at y-axis, shows approximately the median value of variable magnitude on x-axis as shown in figure 4. Figure 4 shows finding median value through frequency curve. Now, application of frequency distribution in geosciences. In geomorphological studies showing area elevation and area slope curves of relief of watershed are the best examples of using cumulative frequency curves. Cumulative percentage of area between zones of different heights are shown for small 3 experimental watersheds, namely Umula, Paham, Siam and Umphar, located in different topographic conditions of Meghalaya plateau as shown in figure 4 and 6. Watersheds are selected because they refer to different topo sequences and are natural units in which natural resources like soil, water and forest may be studied with reference to topo sequences in the Meghalaya plateau. Of course, it is a good model to show the reality of resource distribution, while hypsometric curve shows variations in topographic features of watershed. Distributional features and hypsometric curves are exemplified below. Now examples. Number A, show distribution of annual runoff depth in the Meghalaya plateau for identifying the areas of high runoff availability for its utilization. Frequency distribution of annual runoff depth of 235 watersheds of Meghalaya plateau, which is calculated by classifying total aerial units into 8 classes having class interval of 1000 mm of runoff depth as per following the above given rule of finding number of classes. It depicts a clear picture of aerial distribution that the areas of southern slopes of Meghalaya plateau contain more runoff in the watersheds, which may be utilized for hydroelectric generation. The areas adjacent to Bangladesh border and interior Cherrapunji yield extremely high runoff, that is more than 7000 mm annually, especially during the rainy season as shown in figure 5. The abbreviations in this figure 5 are: number 1 is equal to international boundary, number 2 is equal to state, number 3 is equal to river catchment, number 4 is equal to subcatchment, number 5 is equal to micro catchments, number 6 is equal to water divide between northern and southern slope, number 7 is equal to streams, and number 8 is equal to rivers. Figure 5 shows distributional pattern of annual runoff depth. Now B, relief conditions of sample watersheds selected in Meghalaya plateau and interpretation of hypsometric curves. Number 1, due to relative height of 130 meter in a 1.70 kilometer long Umula watershed, that is in Cherrapunji, the average slope of about 8.0% has been noticed from the mouth of the watershed at 1310 meter to the upper reaches at 1440 meter above sea level. Hilltops are generally flat and dissected by seasonal rivulets and depressions. 2 streams are perennial and others are seasonal, passing through these depressions during heavy rainfall monsoon season. Area elevation curve of Umula shows proportionate area under each category of relative height of the watershed. Number 2, Paham Siam watershed, that is in Nungpo, of about 3.6 kilometer long, that is a straight line section, has a relative height of 277 meter, varying from 533 meter to 830 meter above sea level at its upper flat reaches in eastern part of the watershed. Being located in Inter-Piedmont Valley, the surface conditions of this watershed is relatively smooth. Number 3, relative height of the Umphar watershed, that is in Birnihat, is recorded 360 meter, varying from 80 meter to 440 meter above mean sea level from the mouth to the upper reaches of southwestern parts of the watershed. Killing stream is the main tributary of Umphar watershed that provides regular water supply and influence the pattern of discharge rate. Undulating topography is main feature of watershed. Area elevation curve shows that about 15.0% area of watershed lies at higher elevations. Now see, interpretation of area elevation curves. From the hypsometric curves that is shown in figure 6, there is an indication that the areas of central Meghalaya plateau display a matured plateau relief. For example, the fractional areas under each relative height are almost equal in Umula watershed, which is located on flat lands of Meghalaya plateau, while Umphar watershed of foothills has less percentage of area under the categories of higher elevations as shown in figure 6a. Figure 6a shows hypsometric curves and figure 6b shows area slope curves for the experimental watershed. Now D, area slope curves. Another example of cumulative frequency curve. Slope is an important land surface feature. Its relationship with area in the watershed is significant to study the slope features. It is shown through frequency distribution categorizing slopes by preparing slope maps as shown in figure 7. More than 3/4 area of Umula watershed accounts for slopes of moderate categories below 35%, while a few areas in Paham Siam, that is in Nangpo, and Umphar, that is in Binni Hat, are calculated under steep slopes of more than 100%, that is equal to 45 degree, figure 6b. Flat hilltops with steep valley slopes are topographic features of these watersheds. It is indicative of higher dissection. There is a longitudinal flatland of rice cultivation along with the main stream on the mouth of Paham Siam watershed, while steep slopes are found either near the mouth or near the confluence areas of streams in these watersheds as shown in figure 7. The abbreviations used in figure 7 are, figures in parentheses are in percent. Number 1 is equal to flat, that is below -2%. 2 is equal to very gentle, that is from 2 to 4. 3 is equal to gentle, that is from 4 to 10. 4 is equal to moderate, that is from 10 to 20. 5 is equal to moderately steep, that is from 20 to 35. 6 is equal to steep, that is from 35 to 60. 7 is equal to very steep, that is from 60 to 100. 8 is equal to most steep, that is from 100 to 175, and extremely steep, that is above 175%. Figure 7 shows slope variations in the experimental watershed, a case of frequency distribution showing areas of different slope classes. Now, summary. Processing of collected data and its arrangement in table form are fundamental steps for further application of statistical techniques to infer the results from data. Editing, coding, classification of data and frequency distribution provide accurate and correct procedure for data arrangement. Graphical depiction of frequency distribution becomes important tool for interpretation of geographical distribution. Hypsometric curve, that is showing area elevation relationship, slope depiction, that is calculation of frequency of different slope categories, and mapping geographical attributes are implicitly concerned with the frequency distribution. I hope you have understood the concept of data processing and frequency distribution. See you next time. Thank you.